everyone, my name is Nur Alya Binti Abdul Rahman and my student ID is 24003416.
Hi, my name is Fatimah Muniifah Binti Zamri, student ID 22010239.
Hi, my name is Siti Binti Syamsul Azhar. My student ID is 22010277.
Hello, my name is Nurliana Binti Khairizal with the student ID of 220102999.
Hi, I'm Kok Wey. Student ID 22010492. Hi, I'm Kok Wey. Let me introduce reaction engineering part for the integrated design project. Reaction engineering mainly focus on steam methane reforming process, SMR, to produce hydrogen. Basically, methane and steam first react over a catalyst in a highly endothermic step to produce syngas. This is immediately followed by water shift reaction, which converts the carbon monoxide into additional hydrogen, boosting our final yields. For this facility, we propose multi-pack bed reactor system. This design is superior because it allows us to carefully manage the temperature profile, staging the reaction for optimal combustion. It is perfectly matched with a nickel-based catalyst. The industry standard for its high activity and stability at an intense operating temperature require around 700 to 1100 degrees Celsius. Our goal is to position cooling energy at the forefront to this transition with a state-of-the-art plant producing 30,000 tons of 99.9% pure hydrogen annually.
Finally, to match the 90% conversion that we got from our symmetry simulation, we use the effective rate constant of 3.2 per second was determined. This value falls with the typical range reported for industrial nickel catalysts. These kinetic parameters form the foundation for our reactor modeling and sizing. Our reactor model is a multi-tubular packed bed reformer, which is a standard design in industrial hydrogen plants. Each tube packed with nickel Al2O3 catalyst and heated externally inside a furnace to supply a large amount of energy required for the endothermic SMR process. We use a plug flow reactor (PFR) model assuming negligible axial dispersion and uniform catalyst activity throughout the tubes. Using symmetry, we simulated the system under the following key operating system, which is a temperature of 855.9 degrees Celsius, a pressure of 25 bar, and also a steam-to-carbon ratio of 3:1. Under these conditions, the reactor successfully achieved 90% methane compression, consistent with industrial expectation. Using the Levin-Spiel plug flow design equation, we calculated the required catalytic volume. The final reactor size is 1.544 cubic meters, which is realistic for multi-tubular SMR design.
Now, I'll explain about how to maximize hydrogen selectivity in the process of converting methane into hydrogen. First, let's define hydrogen selectivity. This isn't just about conversion, it's about precision. It ensures that the methane we consume is transformed specifically into valuable hydrogen rather than unwanted byproduct. High selectivity means we use our raw materials more efficiently and achieve a much purer final hydrogen. So, how do we enhance selectivity? Our first key strategy is to optimize process condition. The primary goal here is to promote water-gas shift reaction, which convert carbon monoxide and water into additional hydrogen and carbon dioxide. The most effective way to do is by carefully controlling the steam-carbon ratio by maintaining a ratio between 3.0 to 3.5. This excess steam does two things. It pushes the main reforming reaction forward and creates a perfect environment for water-gas shift reaction, thereby generating more hydrogen. Our second strategy moves from process condition to the molecular level. Advanced catalyst engineering. While nickel-based catalysts are standard, we can make them much softer. The goal here is to actively suppress side reaction that creates impurities. We achieve this by adding promoters such as potassium to the catalyst. These promoters work by neutralizing the acidic sites on the catalyst surface that are responsible for initiating undesirable reaction. In essence, they electronically modify the catalyst to be more selective. Following our look at selectivity, we now turn to this crucial counterpart, hydrogen yield. If selectivity is about the quality and the precision of the process, yield is about the quantity and the volume of hydrogen we get out for every mole of methane we put in. Maximizing yield is absolutely essential for economic viability and overall efficiency. Our first and most direct strategy for boosting yield is optimized temperature management. The core reforming reaction is highly endothermic. It consumes most massive amount of heat, therefore we must feed in energy to push it towards completion. Operating with high temperature of 850 to 90 degrees Celsius is critical. This provides the intense thermal energy needed to shift the reaction equilibrium favorably, significantly increasing the both speed of reaction and also the total amount of hydrogen we can ultimately produce. However, traditional reactors eventually hit a thermodynamic ceiling. This is where our second strategy creates a paradigm shift: advanced reactor configuration. The most groundbreaking approach is the use of membrane reactor. We here integrate hydrogen selective membranes directly into the reaction zone. Their function is simple yet revolutionary. They instantaneously and continuously remove the hydrogen product from the reaction environment. By doing this, we are perpetually offsetting the equilibrium. According to Leach-Latour principle, the system constantly compensates by producing more hydrogen, effectively pulling the reaction forwards. This allows us to break through the conventional use limit. We have discussed how to get the most and the purest hydrogen. Now we address the enemy of a stable long-run process, the side reaction. These are chemical pathways that consume our valuable methane without making hydrogen, and their primary weapon is catalyst deactivation. The most common issue is carbon deposition, or coking, where methane turns into solid carbon that clogs and destroys the catalyst. Our first line defense is strategic process control. The goal is to never enter the thermodynamic danger zone, where cooking is favorable. We achieve this by once again using a high steam to carbon ratio above 3.0. This isn't just for selectivity. The excess steam creates an oxidizing environment that effectively gasifies the carbon precursor, essentially cleaning the catalyst surface in real time. Our second strategy is to build a smart catalyst that inherently resists attack. This is done by incorporating magnesium oxide as a structural promoter. Magnesium oxide works on two levels. First, it creates a more basic surface chemistry that is naturally less hospitable for carbon atom to stick a new plate. Second, it acts as a physical scaffold, stabilizing the nickel particles and preventing them from forming into larger clouds. Our final strategy is simple. It keeps the poison out. Rigorous feedstock purification is essential for our upstream insurance policy. Even trace amount of sulfur can cripple the entire process. We use zinc oxide absorber as a guard bait to chemically scrub the natural gas feed, trapping sulfur compounds before they ever reach the main reactor. That's all for the reaction engineering part. Thank you.
So now, let's start with the context. But before that, I would like to explain what is steam methane reforming, or SMR. SMR is the most common industrial method for producing hydrogen. So let's see the introduction of case study for separation process. First is the hydrogen purification is a crucial downstream step in SMR, and the syngas produced from SMR contains hydrogen, carbon monoxide, carbon dioxide, methane, and water. And in order to achieve 99.9% hydrogen purity, impurities must be removed effectively. So why purification is needed? It is because from the simulation, our raw syngas only contain 36.67 mole% hydrogen, so impurities need to reduce hydrogen purity and damage equipment. Industries require 99.9% hydrogen for fuel cells, chemical synthesis, and refining. Adsorption-based purification is widely used due to first, high efficiency, low energy consumption, and ability to regenerate adsorbents. So let's jump to our main objective. Our primary goal is straightforward but demanding. So first, our main objective is to design a hydrogen purification system capable of achieving 99.9% purity. Second is to identify, quantify, and analyze impurities present in syngas. Third, to select a suitable adsorption-based separation method. Fourth, to determine optimal adsorbent type. column configuration and operating conditions. And last but not least is to design a multi-stage purification process to ensure high hydrogen recovery, stable long-term operation, protection of downstream equipment, and industrial scalability. Now, let's quantify the challenge. To design an effective purification system, we must first identify and measure the impurities we are dealing with. So, the key species formed in SMR is first methane, our unreacted feed, steam, the reactant and major component, hydrogen, the desired product, carbon monoxide, our intermediate product, and last but not least is carbon dioxide, which is the product from WGS reactions. So our assumptions that we use is all gases behave ideally. The gas constant is R equals to 8.314. Our temperature is T equals to 1129.05 Kelvin, and the pressure is 101.325 kPa. The formula that we use is the ideal gas law, PV equals to nRT, and the concentration is C equals to PA over RT. So here is the concentration of species from symmetry simulation that we have calculated for species methane, hydrogen, water, carbon monoxide, and carbon dioxide.
Hello, here I'm going to explain to you the strategy to achieve 99.9% purification efficiency. So the feed that we have here is 36.67 molar percentage of hydrogen gas, and the balances are carbon monoxide, carbon dioxide, methane, H2O, and other traces of hydrocarbons. The target here is to get 99.9 molar percentage of hydrogen gas. So we here have three stages. The first stage is through bulk impurity removal by distillation. So our goal here is to remove 90% of bulk impurities, and in result we get to increase the percentage of hydrogen gas by 37 to 38 molar percentage. Next is stage 2, which is absorption column, which is methane, carbon dioxide, water residual polishing. Adsorbent that we're using here is zeolite 13X, and it is a sodium form aluminum silicate with 10 node pore openings, has high affinity for polar and quadrupolar molecules, and also it has higher capacity for all the impurities than 5A or activated alumina. So the operation is by fixed bed near atmospheric pressure, and the target here is residual water, carbon dioxide, H2S, mercaptans, and partial methanes. So basically the performance here is to remove 90% of all the impurities and increase the concentration of hydrogen gas to 80 to 90 molar percent. And through regeneration, we use pressure swing or low temperature thermal swing. So next, I'll explain to you the stage 3, which is pressure swing absorption PSA for final purification. We are using 20 to 25 bar of absorption pressure and deep vacuum desorption about 0.1 to 0.5 bar. The target here is the residual carbon monoxide, carbon dioxide, and methane. Basically, the performance that we want here is more than 99.9% removal of all the impurities, and the final hydrogen purity is more than 99.9 molar percentage. For regeneration, we are using 2 to 3% of purified hydrogen gas, and the benefit of this stage is the zeolite 13X stage reduces impurity load on the PSA, ensuring efficient cycling and stable hydrogen recovery. So all of the data I mentioned before is by our reference as mentioned below. So next, I will explain to you the absorbent selection and column design. So absorbent selection for SMR purification is to protect the downstream nickel reforming catalyst. Our primary absorbent is zeolite 13X, which is often used in layered configuration preceded by activated alumina. It is selected because of its uniform pore size and effectively removes key catalyst poison like H2S and mercaptans, and provide final dehydration of the feed. So the outcome of the zeolite 13X to ensure high catalyst longevity, operational stability, and efficient production of high purity hydrogen. So we are using two-tiered purification safety strategy. Initial absorbent system, which is to safeguard the reformer catalyst from poisons, and second is downstream PSA, remove carbon monoxide and carbon dioxide produced by the reforming and shift reactions which compete with hydrogen and reduce its purity and recovery. Moving on to isotope model installation. So basically, we're here to determine the best fit isotope model for carbon dioxide absorption on zeolite 13X. So the method we are applying here is to gain experimental data from our literature reading, which is Carbonati et al. 2004, and then the pressure from the experimental data is converted to concentration using ideal gas law. So both Langway and Freundlich models are linearized and fitted. We are using ideal gas law in order to make the calculation is easier and more efficient. For the Langway isotope model, we got the linearized equation, which is 1 over Q equals to 13.53 1 over C plus 0.2395, and the R square is 0.9694. For Freundlich isotope model, we get the linearized equation, which is log Q is equal to 0.3006 log C plus 0.2972, and the R square is 0.9769. So here are our graph. As you can see here, that the Freundlich isotope model show a better fit line where the R square is higher and more accurately describe how carbon dioxide are absorbed on the heterogeneous surface of zeolite 13X, making it more reliable for our industrial system design. For mass transfer zone and column sizing, we're here to determine the optimal absorption column dimensions for carbon dioxide removal using zeolite 13X. So basically, MTZ is the region in the absorption bed where active absorption occurs. So here is our calculation in order to find the bed diameter, which is using the formula of MTZ length over aspect ratio, and we got 0.038 meter. And here is actual column height using the formula of MTZ length over use factor, which we get 0.20 meter. So the design basis that we get is mass transfer MTZ 0.5 length is assumed for carbon dioxide on zeolite from the literature study that we find, and bed aspect ratio is got 4 for proper flow distribution, also from literature reading, and use factor is 0.75 applied using the standard value from our literature reading. So using all the information that we get, the design outcome is actual column length is 0.20 meter, actual column diameter is 0.038 meter, the MTZ length is 0.15 meter, and the unused bed is ensure the bed height accommodates the MTZ while maintaining the 75% bed utilization at breakthrough.
Now I will talk about multi-stage purification effectiveness. After the steam methane reforming process, the syngas exiting the reactor contains around 36.67 mol% hydrogen, along with impurities such as carbon dioxide, carbon monoxide, methane, and water vapor. To achieve the required hydrogen purity of 99.9%, a multi-stage purification system was designed. The first stage is distillation, which removes about 90% of the bulk impurities, primarily methane and water, due to their significantly higher boiling points compared to hydrogen and carbon monoxide. This step protects the adsorption beds and prepares the syngas for deeper purification. Next, the gas enters the zeolite 13X adsorption column, which removes the remaining carbon dioxide, moisture, and light hydrocarbons. Using the Freundlich isotope model, the total absorbent mass required for full-scale operation was calculated as 4,452 kilograms. This ensures sufficient capacity for continuous operation. The third purification stage is pressure swing adsorption, or PSA. Here, the remaining traces of carbon monoxide, carbon dioxide, and methane are removed under high-pressure adsorption and low-pressure regeneration. The PSA unit is responsible for the final polishing of hydrogen stream. Finally, the purified gas undergoes fine filtration, which removes ultrafine particulates and ensure the gas meets product quality standards. After all stages, the system successfully achieved a hydrogen purity of 99.91%, exceeding the target specification. In conclusion, the entire design was developed to meet the strict requirement of producing hydrogen at 99.9% purity. This purity specification guided the sizing of the reactor, the purification units, and the overall process configuration. On the reactor side, the SMR reactor operates at 855.9 degrees Celsius, 25 bar, and a stream-to-carbon ratio of 3. These conditions allow the system to achieve 90% methane conversion, and the reactor volume needed was calculated as 1.544 cubic meters using the 11 spill method. The separation system consisting of distillation, zeolite 13X, adsorption, PSA, and fine filtration works in sequence to progressively remove impurities until the hydrogen product meet the quality requirement. Finally, the integrated system produced hydrogen at a final purity of 99.91%, confirming that the design not only meets but slightly exceeds the specification. Overall, the process is efficient, technically feasible, and suitable for large-scale hydrogen production.